This is the third part of section 5.4 in discrete mathematics, talking about how to use the technique of generating functions to find sequences an. Suppose we're given the recurrence relation an equals to 3, an minus 1, which has the standard form an minus 3, an minus 1 equals to 0 if you simply subtract this term from both sides. Okay, and the initial term is given a0 is actually 1. Now to start, I will just write out the general form of generating function f of x for the sequence an, which says f of x equals to a0 plus a1x plus a2x squared, and so on. In general, that's an x to the n. I also wrote down what's in front of this. Just remind me, before that, in a coefficient, it will be denoted by n minus 1, and the term of that is x to the power of n minus 1. But you don't have to write it down. Just keep that in mind. Okay, suppose, imagine this term exists there, because we actually omitted a lot of terms here and here. Next, I'm going to multiply my f of x by 3x. The reason I want to choose the constant 3 is because of that. Okay, so I'm going to multiply f of x by 3. And the reason I choose x is because the indices here has been decreased by 1 in order to have n minus 1. So the difference between these two indices is actually 1 unit. That's how I choose the power of x. Okay, for the same idea, let's jump to example 3. When we have this recurrence relation, after we have f of x for the general generating function of an, we will also need to calculate 5 times x times f of x, and then we will calculate 6 times x squared times f of x. It's x squared because this is n minus 2. Okay, so that power of x actually agrees with whatever we're subtracting here down in the indices. Okay, we'll see why we want to multiply the 3x here later in the next step. Okay, but once we do this, we will see that the first term becomes 3x times a0, which is 3a0 times x. I'm going to place that term down here because I want all the x terms lie in the same column. And similarly, when I multiply 3x into this f of x, I'm going to have 3x multiply that second term, gives me 3 times a1 times x squared. I'm going to list that down here for x squared terms. Okay, when you combine 3x with this term in front of the anx to the n, you will see 3x times a sub n minus 1 times x to the power of n minus 1. Combine those two x terms, we will see x to the n term, which makes it 3a sub n minus 1 because of that, times x to the n. Okay, and again, these terms continue. Now, we're going to subtract these two equations, left by left, right by right. And I am doing the subtraction simply because of the sign here I see is a minus sign. Okay, if that's an minus 3a n minus 1, I'm going to follow the same pattern here for generating functions. Okay. Now, if I subtract the left by the left, we are going to see f of x minus 3x times f of x, which can be easily simplified if you pull out f of x. And if I subtract the right-hand side by the right-hand side down here, an minus 0, that's going to be a0 minus 0, that's going to be a0 by itself. And then to subtract these two terms for x, I can pull out the x and just subtract the coefficients in front and have a1 minus 3a0. That's this term. And similarly, you could combine all the terms with the same x power. In general, for the nth power of x, we will have an minus 3an minus 1, which is right here. Okay, the secret that we want to do these operations beforehand is because look at what we have down here in the result. This coefficient is exactly the term when you substitute n equals to 1 into the recurrence relation, right? And this is exactly the form of the recurrence relation when n equals to 2. And that's in general the case for n equals to n, of course, right? So according to the recurrence relation, each of these coefficients are zeros, which makes it quite simple for our right-hand side. And also a0 is given as 1, so I'm going to substitute it right here. My right-hand side is now just as simple as 1. And left-hand side, again, if we pull out f of x, it's 1 minus 3x in front. Now we can solve for f of x. And we have 1 over 1 minus 3x. Remember how to write this out as the expanded term? The expanded expression for that will be 1 plus 3x plus quantity 3x squared. In general, that's going to be 3x as a quantity to the power of n. Again, as a quick reminder, you want to refer to this identity in order to write out this form, okay, in order to do this step. Alright, let's move on to simplify what we have here. This is 1, this is 3, this is 3 squared times x squared. Okay, so we have the list of coefficients as 1, 3, 3 squared, 3 cubed, and so on until 3 to the n, and go on. Do you see the sequence an in its complete form? An is 3 to the n. I hope this is not a surprising result for you, because we've already know this is exactly a geometric sequence, and we also discussed how to use characteristic equation to solve for this recurrence relation, right? Okay, now you could try to apply the same technique to example 3 and pause the